Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be starting with something which is known as DP on grids, or you can say DP on 2D matrix, or something similar to which has n rows and probably not m columns, but similar to that is what we will be starting with. So to start off with, we will be solving problems how to count paths. Then we will be solving problem how to count paths with obstacles. Then obviously we will be doing something as minimum path sum. Now these questions are all asked in big tech giants. Okay, so right after that we will be doing something like max path sum, but this will be under certain conditions. It won't be the standard way. Right after that we will be doing the triangle problem, and after that again we will be doing one similar problem which will be having two start points with two people, just to understand how to elongate. So I'm very much sure after you do all these six problems, because all these six problems are of different types, if you have done all these six problems, you can do any problem on DP on grids or on 2D matrix. This is my promise to you. So you just need to make sure all the six problems is what you need to watch and submit. Now I'll be leaving the Code Studio link out over there in the description. You can definitely submit over there. Just in case if you want any other platform, you can just take up the question name in the title, and you can do a Google search if you want any other links. But yeah, I'll highly recommend you to try out Code Studio, because it's a wonderful platform and something which is from India, so we should definitely support it. Now, what are the prerequisites for DP on grids? I will highly recommend you to watch the lecture 7, as I always say, because over here I've taught you a trick where I've told you that if you're writing a recursion function and you have to count ways, how do you do that? You write a base case, and in that base case, you either return a 1 or either you return a 0, depending on if your conditions are met or not. And then you take whatever recursions you have, like how many number of recursions, and then you return L plus R. So if you remember these ways, that's how you count ways. In the lecture 7, I've deeply taught you this. So if you don't know about this, please watch it out, because without this, recursion on grids or DP on grids will not be easy for you. So please watch it before starting off with DP on grids. So to start off with, let's check out the first problem, which is total unique paths. Now, what are they saying? They're saying you're present at point A, okay, which is the top left cell of an M cross N matrix. Top left cell of an M cross N matrix. Your destination is point B, which is the bottom right cell of the same matrix. Something like 0 comma 0 will be the top cell, and the bottom will be M minus 1 and N minus 1 for sure. Your task is to find the total number of unique paths from point A to point B. In other words, you will be given the dimensions of the matrix as integers m and n, and your task is to find the total number of unique paths from the cell 0 0, like the point 0 0, to n minus 1 and m minus 1. For an example, if I give you a matrix of 2 cross 2 size, the number of unique paths will be 2. Let's understand this question in deep. Okay, so if I'm saying that I'm giving you a 2 cross 2 matrix, okay, so this is the 2 cross 2 matrix definitely. And over here, if I'm saying you started this is your starting point, this is your ending point, because if I write down, it states from 0 0 to 1 comma 1, because that is the right bottommost cell. So how can you basically move this guy? Now remember, in the question it clearly states you can only move right or you can only move down. No other movement is allowed, only right or only down. So if you move right, you will end up reaching here, and then again if you move right, you will end up reaching here. So that's one of the ways. And I can see the other way is you can decide you will move here and you will reach here. So I think there are a couple of unique ways in which you can reach from 0 0 to 1 to 1. Okay, so if there are two unique ways, you have to return me two. So how do you do this problem? Now if you remember how to write recurrence, that is something which I taught you. how to write a recurrence. That is something which I taught you. But before that, we have to analyze why recursion, right? So what are you doing? You're starting from something like 0 comma 0, and if I just write it in a generic way, you're starting from 0 comma 0 and you're wanting to go till m minus 1 and n minus 1. That is what you are looking to do. Am I correct? Right, I'm absolutely correct. Now, can I say you're basically trying out all possible ways to go from 0 0 to m minus 1 n minus 1, all possible ways. Now, whenever you try out all possible ways, what have I taught you till now? All possible ways means apply recursion, as simple as that. Because if you have to count all possible ways, I'll try all ways and I'll count them, as simple as that. After that, DP and all that comes afterwards. But if I'm being asked to count all ways, I'll try all ways, as simple as that. I'll try one way, two way, three way. I'll keep counting. In this way, I can get the total number of ways, right? So that is what I'll do. So what is the question? How to write recurrence? Now, in our 1D DPs, I've taught you how to write recurrence. What is the step one? Express everything in terms of indexes. Remember this? Express everything in terms of indexes. But over here, instead of index, what will you do? It's a 2D matrix. So obviously, indexes will be two indexes. One is the index I, which will represent the row number. One will be the index j, which will represent the column number. So slight change in the three rules. Over here, express everything in terms of I and j, where I is basically row number, j is basically column number, right? Next, explore all paths or do all stuffs, whichever you call it. Do all stuffs, the point number 2 stays the same. If I'm counting always, sum up always. If I'm looking for max or minimal, I'll take the max or minimal. Depending on the question, if you're being asked to count all the ways, you sum up all the ways. If you're being asked to count max and minimal, you'll count the max and minimal. Okay, depending on your question, you're going to do this. So simply follow these three steps and you can write the recurrence for any 2D grid. And after that, the steps are very easy to convert a recursion to DP, to rather memoization, and then to tabular DP, and probably after that to space optimization, right? So let's get started. So what was the question? The question was stating how many ways are there in order to reach from 0 0 to n minus, or rather m minus 1 n minus 1. That was the question, correct? So can I say, let's assume I write a recursion f of ij. I write a recurrence f of ij where it tells me the number of unique ways, in which I can reach from 0 0 to I comma j. Specifically, what I'm saying is, if I'm taking a grid like this and assume this is my ij, I'm asking in how many ways. So what I'm saying is, in how many ways can you reach from here to here? So basically, I'm trying to figure out the answer for this particular matrix. That is what f of ij is signifying. It's trying to figure out in how many ways can you reach from here to here if I and j is this, right? So where will we start off with? We will definitely start off with f of m minus 1 and n minus 1, because this is f of n minus 1 and I want to find in how many ways can I reach from here to here. So the entire matrix, right? So I can say I'll start off with I comma j, where the initials of I comma j will be m minus 1 and n minus 1. This is generically how you determine where to start off with. Okay, so that's what I've done. What's the first step in recursion? It's the base case, right? So if you remember the lecture 7, in lecture 7, I think I've told you, how do you count ways? In order to count ways, you have to determine a base case that returns 1, correct? So in the base case, if you have reached your destination, you return 1, or you return 0 if you haven't reached your destination. That's your base cases. If you have reached your destination, you return 1. If you haven't reached your destination, you return 0. That's what I've taught you in the lecture 7. So why don't you do that over here? So what I'll say is, okay, I know my destination is very straightforward. If I'm starting from n minus 1, m minus 1, or rather the opposite, m minus 1 and m minus 1, I will have to go in such a way that I reach this particular guy from here, correct? So I know this is the base case where I reach 0 and 0. So straight away, say if I is equal to 0 and j is equal to 0, if that's the case, I definitely know I have reached my like the destination. And if I've reached my destination, I know the recursion would have taken a path and it would have reached here. So why don't I count that path? So I will say return 1, because on returning 1, it gets counted. Lecture 7, guys. Lecture 7 of recursion series. Okay. So that's how you can easily count it, correct? Now, what is the other base case? Assume you are standing at m minus 1, n minus 1, and there is 0, comma 0, and you kept moving up, kept moving up, kept moving up, kept moving up, and you exceed the boundary. Or it might be the other way, you kept moving left, you kept moving left, and you exceeded the boundary. So you can either exceed the boundary in the upward direction, which means the row number goes lesser than 0, or the column number goes lesser than 0. Very straightforward. So what I can say is, if the row number goes lesser than 0 or the column number goes lesser than 0, that path is something which is not a path, because it took you out of the boundary, and I wanted to travel inside the matrix in order to reach from m minus 1, n minus 1 to 0. So you got out of the boundary, right? So what you will do is, you will say, I will not count this path. This path is not under my count. So I will return 0. Make sense? That's what I've done. So the base cases have been written. Remember this. These are the base cases that I've written. So express in terms of index and write base cases. That's a step 1. So what I've done is, I've made sure the step 1 is complete. What is this? Explore, do all stuffs. Now what is all stuff over here? Let's analyze. The question stated the guy can move in the rightward direction or in the bottomward direction. So if you're moving from the bottom, yes, if you're moving from the bottom, we can say it's the opposite. Yes, we can say it's the opposite. If you're moving from here to here, I can say the right one will be either you can move left, either you can move upward. It is exactly the opposite. So if it's exactly the opposite, just do, because there are two ways. One is up, one is left. Instead of bottom and right, over here it's up and left. Why don't you explore it? So I can say, okay, I have couple of ways. One is the upper way, where I will say, okay, I will move to, if I go up, what happens? The row reduces. Again, very basic stuff. The row reduces and the column stays same. If I go left, what happens? The rows, because if I'm going left, we are still in the same row, but we are moving a column back. So thereby j minus 1. Correct? So we have done this, and so explore all possible paths is also done. What's the next step? Sum all the ways, because you've been asked to count the total ways. So kindly sum up all the ways. So why don't you sum up all the ways? So what I will do is, I will say return up plus left. So what I've done is, I have returned up plus left. So I've summed up all the possible ways over here. And this is what a recurrence will be. Yes, this is how you can easily write a recursive solution. So very straight, very straightforward. Express, explore, sum up, or whatever is the question stating. That's how you do DP on grids. So since I've done this, we have done recursion, right? And we know that for every index, yes, and for every index we are exploring two possible paths, correct? So I can say the time complexity of recursion. How many ways are there? Like, how many boxes are there in the matrix? M into n boxes. And for every box, you're taking two paths: up, left, up, left, up, left, up, left. So if for every boxes you're taking two paths, can I say all the boxes in total? Yes, all the boxes in total will be having 2 into 2 into 2 into 2 into 2 into 2 paths, which is 2 into m into n paths. So the time complexity is this, which is exponential in nature, right? Space complexity is a recursive stack space, which will be the path length, which will be the path length. Remember, the space complexity will be the path length. Why? Because if you're wanting to reach here, let's say from 3 comma 3, the path length will be, you will go to 2 comma 2, then you will 2 comma 3 rather, then you'll go to 1 comma 3, then you'll go to 0 comma 3, then you'll go to 0 comma 2, then you'll go to 0 comma 1, and then you'll go to this. So the path length contains 1 length, 2 length, 3 length, 4 length, 5 length, 6 length. So it's basically the path length is nothing but m minus 1 plus n minus 1 is the path length, because over here you took, if you see carefully over here, if the length was 4, you ended up taking 3 upward directions and you ended up taking 3 leftward directions, right? Thereby the path length is this. So this is the recursion's time complexity and the stack space complexity. Now, what's the next step? What's the next step in recursion? I have told you easily. How do you optimize recursion? In order to optimize recursion, what you generically do is you try to convert that into a possible DP solution, correct? And how do you do this? In order to do this, you try to do something which is known as memoization, correct? But when can you apply memoization? If there are overlapping sub problems. Yes, if there are overlapping sub problems, you tend to apply something like a memoization. So why don't we do that? So what I'll do is I will take m equal to let's say 3. I'll take n equal to 3 and I'll try to figure out how many total ways are there, correct? So practically speaking, this is how the grid will look, and you want to find how many ways are there to reach from this particular position to this particular position, right? So let's do that. So this is 0 1 2, this is again 0 1 2. So we start with f of 2 comma 2, correct? Now where can f of 2 comma 2 go? It can either go to the upward direction, which is definitely f of the row numbers reduces by 1 and the column stays the same, or it goes in the leftward direction where the row number stays same and the column number reduces by 1, correct? And if you know, in recursion, if this is the upward direction, this is the leftward direction, which recursion will be occurring first? Obviously this recurrence will be occurring first. So let's do this recurrence. Now f of 1 2, where can it go? It can definitely go to something as f of 0 2, and it can definitely go to something as f of 1 comma 1. So this is the upward direction, this is the left direction, this is the up, this is the left. Now where can f of 0 2 go? It can again go to the up. So if it goes to the up, it's minus 1 comma 2, and if it goes to the left, it's basically 0 comma 1, correct? So what happens over here? Whenever you reach f of minus 1 comma 2, what happens over here? So if you remember, the moment the row goes lesser than 0, there was a base case as I lesser than 0 or j lesser than 0. If any of these things happen, you end up returning a 0. So you end up returning a 0 over here, correct? Over here there is something like f of 0 1. Again it can go up, which is minus 1 comma 1, or it can go to the left, which is 0 comma 0, correct? So minus 1 comma 1 will again is the upward direction, which will return 0, and this guy ends up returning 1, because this is where your destination is, because this is where your destination is. You have reached f of 0 comma 0, so that thereby this is your destination. So how will the recursion be like? F of 0 comma 1 would have called up, would have called left. So the up would have been minus 1 comma 1, and the left would have been f 0 comma 0. This guy gets 1, this guy gets 0, and in order you return the summation of both, which is 0 plus 1. Thereby this guy gets a value of 1. So I can say this guy gets a value of 1. So you can easily return that value 1, correct? So thereby let's quickly erase this and try to solve this recursion. Now you're at f of 0 2. Now, at f of 0 2, what would have happened? It would have gone to up, which is f of minus 1 2, which gave him 0, which gave him 0. It would have gone to left, which would have gave him f of 0 1, which is 1. So thereby it returns 0 plus 1, makes it a value of 1. So it returns a 1. So let's quickly erase it. So this is how it will be. And in the next step, yes, in the next step, what happens? There is something like f of 1 2. It goes up and now it goes left. So f of 1 1 will be something like f of 0 1, because it has to go up. And similarly, it will be like I have to go left, which will be f of 1 0, correct? So if you carefully see, we get our first sub problem. 0 1 has been solved here. So there is no need to go further down into f of minus 1 1, which is the top, and there is no need to go to the left. So I got my first sub problem. Thereby I see there are overlapping sub problems, and if there are overlapping sub problems, what can we apply? We can definitely apply memoization. And what is the shortest trick that I've told you to apply memoization? Just figure out which is the changing parameters. So there were a couple of parameters, correct? One parameter was I, the other parameter was j. So if there was a parameter I which is changing, there's a parameter j which is changing. So what is the i's maximum value? I can say it's m minus 1 because that is where we start the recursion call. What is the j's maximum value? N minus 1 because that is where we start the recursion call. So I can say if I require the index m minus 1, I will have to declare an array of size m, because if I declare an array of size m, I will get the index m minus 1. Similarly, in order to get an index n minus 1, I have to declare an array of size n. So basically I can say I will be requiring a dp of m cross n, which is a 2D dp of m cross n. So if I have a 2D dp, I can convert this into a memoization solution. So how do you convert this into a memoization solution? Again, very straightforward. Step 1, declare the dp. Declare the dp of size m n. If you're using Java, you can easily do this. If you're using C++, you can declare a vector. And make sure everything is initialized with minus 1. That is something which we have to do to make sure that we understand that these values have been previously stored. After this, what is the step 2? Store the answer that you're returning. Store the answer that you're returning. So kindly go across and store the answer. So let's store the answer over here. dp of ij equal to up plus left. Next, step 3. Whenever there is a call, please check if that answer has been previously stored or not. If yes, kindly return dp of ij. That's how you can easily convert a recursive solution to a memoization solution. And if you've converted a recursive solution to a memoization solution, the time complexity will be no more exponential. Rather, it will be the number of states, because at max you can have a call for 0, 0, 0, 1, 0, 2. Like what calls can you have? If I ask you on a very generic term, you can have a call for 0, 0, you can have a call for 0, 1, you can have a call for 0, 2, 0, 3. Similarly, you can have a call for 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, and so on. So I can say at max you can have n cross m. Like what are the maximum calls of f of ij you can have? You can have at max of n cross m calls for recursion. Thereby the time complexity is this, and the space complexity is still a recursion stack space, which is the path length, and the path length is n minus 1 plus m minus 1. That's the path length, plus a big O of n cross m for the dp array that you're using. So we have boiled the time complexity into much better than exponential, and this will be accepted. So if you are in an interview, you can stop over here. But I will highly recommend, if you get these kind of problems, go to the tabulation, go to the space optimization, eat as much as time as possible, because if you know the problem, if you can solve the problem, it's better you impress the interviewer by that one problem in such a way that he'll be like, wow. Okay, but if you stop at memoization, he might start asking. Instead of him asking, you impress him. Got it? So we have pretty much done the memoization form. What's the next one? The next one is tabulation. Why? Because we still have a recursion stack space that is being used, and this somewhere might give you TL. So I don't want this extreme recursion stack space to be used. So I want to omit this. That's where we have to think of something as tabulation. So what did I teach you for tabulation, if you remember? Whatever is the base case in recursion, just write that. What is the base case over here? It's states I equal to 0, j equal to 0, return 1. So go over here. First of all, to declare an array of size dp of nm. First of all, declare an array of size dp of n and m. What is the next thing that you will do is very straightforward. It's you will be like, declare the base case of 0, 0 to be 1. Okay, so that's one of the things. What is the other base case? The other base case stated I lesser than 0 or j lesser than 0. Now this cannot be expressed in dp, so ignore this. We will deal with it separately. So what is tabulation? What is tabulation? Now a lot of people will say tabulation is going from bottom up. But do you understand the meaning of bottom up? Do you understand the meaning of top down? That's very, very important. So do you understand the meaning of tabulation? Now, a lot of people will say tabulation is bottom up, and they have a tendency key bottom up means going from 0 to n or something like this. Let's understand what is tabulation. So tabulation is basically, what is recursion? Why do we call a recursion a top down approach? Let's understand. If you carefully observe in the recursion, the call was made from here. You went down, you went down, you went down, and then you solved this base case. Then you accumulated the answer, and came back, and this got its answer. So you went down, 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 and you got your answer, and the top guy got his answer by going down, thereby top down. The top guy got his answer by going down. But in tabulation, it's the opposite. You start from f of 0, 0, 1, then you accumulate, then you take this, accumulate, take this, accumulate, take this, accumulate, and you ultimately reach f of 2, 2. So you start from the down, which is bottom, and you go to the up. So you go from down, 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 down to up. So down, up, or bottom, up. That's why tabulation is known as bottom up. Got it? Don't, it's not key. You go from 0 to 1. It's basically you start from the base case, you accumulate, and you go and reach at the top pinnacle, and you get your answer. That's why we call tabulation as the bottom up approach. So we have done this, right? What's the next thing we have to understand? So we have written the base case. In 2D DP, it's very important to understand what are the states. I'm saying the states are ij. What can be the possible first value of I that you have to think? You'll be like, Striver, the first value of I will be 0. I'll be like, yes. But for this row 0, what can be the j value? It can be 0, it can be 1, it can be 2, it can be 3, dot, dot, dot till n minus 1, right? Next, what can be the value of I? It can be 1. For this j will be 0, 1, 2, dot, 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 dot till n minus 1. What can be the next i's value? It can be 2. For this j can be 0, 1, 2, dot, 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 dot till n minus 1. So you're getting the states are like, there is a state of row. That's for sure. There is a state for the row number which starts from 0, goes on till n minus 1. And for every row number, there is a particular column number. Correct? For every row number, there is a particular column number which goes from 0 to n minus 1. Correct? So we know this for sure. We know this for sure. So just write, express the states. Remember the step 1 to convert. I'll write the steps so that it gets easy. The steps to convert a memoization to a tabulation is very simple. Declare base case. Express various states in for loops, or rather all states in for loops. 3, copy the recurrence and write. So step 1 is done, which is declare base case. Step 2, express all states in for loop. Over here there are 2 states, so 2 nested loops will go. Copy the recurrence. Let's copy the recurrence. What is the recurrence? So can I say, I know one thing. If I will be 0 and j will be 0, we have already expressed it. So probably we can say if I is equal to 0 and j is equal to 0, there is no need to do anything. You can just continue, or you can probably write this only. The better way will be to write this only. dp of 0, 0 will be 1. Like, instead of over here, you can directly write it. Or else, if it's not the case, then probably you can think of. Now let's analyze over here in the recurrence. In the recurrence, we see if I is equal to 0, j is equal to 0, we stop here. But if it's not, then what we do? We go to this line which says f equal to f of I minus 1j, left is equal to f of I j minus 1. Correct? Just copy these two lines. Okay, don't think, just copy. up is equal to, it states, instead of f, it will be dp I minus 1 j, just write it. Left will be dp I comma j minus 1. So instead of f, instead of parameters, I express them in 2D arrays. Because in recursion, what happened was, in recursion, it went down, solved this. Then again went down, solved this. But over here, this guy is already solved. And it is stored in a DP array. It is already stored in a DP array. So just use those values now. Instead of going and calling and solving it, use those values. What you did after this? Up plus left in recursion. So up plus left, and where did you store it? In dp of I j, right? That's what you do. And this is how you can easily write the tabulation. Easy, super easy, isn't it? So I've written the tabulation quite simply. Again, C++, Java doesn't matter, pseudocode matters. So I've written the tabulation very easily. Now the question arises, a straightforward question will arise, but Striver, what if I is 0? This I minus 1 will be a problem. I agree, I agree. So just make sure you probably can give something like if I is greater than 0, and probably something like if j is greater than 0. Simple. Then only we will take these cases, otherwise no. Simple. And if I is greater than 0, we will take it, or we will take upward to be 0. Like I'll show that in the code. When we do the code, I'll show it. We can initially keep upward equal to 0, left equal to 0. And if these two cases are true, then it will modify those answers. And this is how we will do it. Now if you remember, in the recurrence, we started with f of m minus 1, n minus 1, and then we split and got the answers. So if m minus 1 and n minus 1 is the ultimate answer, over here the ultimate answer will be stored in dp of m minus 1 and n minus 1 only. Thereby, you get your answer. That's how you do tabulation. So once you've done tabulation, what is the time complexity? Time complexity is now n into m, because you're just running couple of nested loops. What is the space complexity? Just n cross m for the space used. No recursion stack space, none of it. That's how you get the time complexity and the space complexity, right? What's the next step? The next step is space optimization. Can we do a space optimization? What did I tell you in space optimization? I told you, Striver, if you see at any moment, we are using the previous row. We're just using the previous row. And we're using previous column. If there is a case of previous row and previous column, then we can definitely space optimize. So remember the space optimizations concept. If there is a previous row and previous column, we can space optimize it. Remember this. That's the golden rule. That's the golden rule. Yes. Now, do you need this for interview? The answer is no. I will recommend, if you don't want to learn it, you can stop over here. You can stop over here. There is not an, it's not a necessity you know space optimization. Just because I used to do CP, I know this so well, but it's not required in interviews. Generally, the interviewers will also not be knowing space optimization, so you can ignore it because they won't be rejecting you on the basis of this. So you can stop the video if you don't want to learn space optimization. But I'll still recommend you to learn. Who knows, the interview might be, yeah, understand, right? Okay, cool. Let's understand. So what am I writing? I'm specifically writing, like if I write dp of ij, I'm basically saying, what am I using? I'm using dp of the up, which is j. This is basically the up, and the left, which is basically I and j minus 1. This is the left. That's what I'm using. Correct. So when I'm starting off, let's draw the matrix. When I'm starting off, if this is the matrix in the DP array, how is the for loop running? The for loop is like I equal to j and j equal to j. So the for loop will be like, first it will go here, then 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 here, 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 and so on, so on, so on. So the for loop basically goes in this way and fills up the DPR in this version, correct? And we know this value. We know this value for sure. We definitely know this value, which is 1. Then we go across and figure this value. But for this value, will there be an up? For this value, will there be an up? No. So probably we can keep it as 0. Right? We can initially, remember this, we can initially start off with a dummy DP guy. Dummy DP of n size, and we can initially keep it as 0, 0, 0, 0, 0. Kept. Next, we can probably say this as temporary, and we can start storing it. Whatever value you get over here, assume you get 1, assume you get 1, assume you get 1, assume you get 1. Just assume you're getting 1. So you store it over there. Correct. Next, this is the value that you have to compute.
Sorry, I can't read that.
Thereby, you come to the next row. When you come to this pink row, and when you try to compute this guy, who is your up? This guy is your up. So can I say you no more require this? You no more require this. You just require the value. For this guy, you require the value stored at here. For this guy, you require the value here and here. For this guy, this is the upward, this is the left. For this guy, this is the upward and leftward. For this guy, this is the upward and leftward. So you just require this green. So can I say, I will now say this guy to be DP and this guy to be the temp, and I can easily do my job. Once this is computed, assume this is computed like 1, 2, assume something like this, 3, 3, 4, assume, just I'm randomly picking up values. Next, if you go to this guy and you're trying to compute this, you'll require this guy's, this value and this value. Thereby this becomes DP. So can I just store the previous row? Can I just store the previous row? Can I just store the previous row? Because if I'm storing the previous row, whenever I'm at the current row and I'm trying to compute, let's say this guy, I'll require this guy and this guy. This guy I can easily get by row, and this guy I'll easily get by previous row. Because in order to compute this, there is no requirement of this guy. There's only requirement of this up and this left. Thereby, we can always space optimize it. Got it? So we can always space optimize. That's the proof. Now what I'll do is, I'll try to show you how to space optimize now. So the best way to space optimize is this. Initially, you declare a DP of n, initialize it with 0. Because initially, what did you require? You required this portion. So DP of n declared, right? DP of n declared. Next, you are trying to compute this. So let's quickly write the same code without doing any further stuffs. Let's write the same code, which is j equal to 0 to n minus 1. And I know for sure if I is equal to 0 and j is equal to 0, we're going to say dp of ij equal to 1, and we're going to continue else. Now, what was I actually writing? I was writing something as a dp of ij, right, equal to dp of I minus 1. I'm not writing the cases, like it might exceed, but yeah, I'm not writing. This is what I'm writing, right? Now let's analyze. Instead of dp of ij, let's try to compute this particular row only. Yes, let's try to compute this particular row only. So it's a row. So this is the row. This is the particular row that it's computing. So what I'll do is, I will now say temporary of n equal to 0. And instead of this, I will write temporary of j. So I'm computing that particular row. Now over here, it's the previous guy. Remember this, it's the previous guy. dp of I minus 1 means previous row. And I know the previous row is dp. So what I can say is, I can directly go to previous row. I don't need I minus 1 any further. Because the previous row is dp itself. So I can write dp of j, the previous row, or I can just declare it as previous, right? And this dp It's saying on the current row, the previous column. So what's the current row? The current row is temporary. Current row is temporary. So you can be like, okay, I do not require, I do not require to go any like dp something. I can just call the temporary to get the previous. So dp of j plus temporary done. Once, remember this, once you have computed this particular for loop, the entire row has been computed. And next, the I will increase. So this temporary becomes the next previous. So you can just store it. You can just store it, right? So what you'll do is when this is getting computed, next when you go to the next I, you make this temporary to the previous or DP, whatever you can call it. In this way, you can easily space optimize in an 1D array. Yes, you can easily space optimize in an 1D array. It is as simple as it can get. Now, most of you might not have understood this. I'm not sure if I was so good that you have understood in one go. Just in case you did not, what I'll recommend is do a dry run of the for loop by yourself. Do a dry run of for loop by yourself. Okay, and fill up and fill up. You will understand everything and fill up. You will understand everything why we do not require the entire grid. You will understand yourself. Okay, so as usual, now let's try to code it and show all of the codes just to have a quick revision. So what did I say? You're given m and n, right? So you can say int f, int I, int j, and you can be like, okay, if I is equal to 0 and j is equal to 0, we return 0. We return 1 rather. So just return 1 to count the steps. Or if this is the case, you say it's not possible, return 0. The up will be quite simple, and the left will be again quite simple, which is I comma j minus 1, and you can easily return of plus left. Why? They just check if the answer, do they require modulated answers? No, so it should be fine. You can say return f of what, m minus 1 and n minus 1. If you just do this simply, I think you should be getting an answer. Let's quickly run this code. You see it's running fine, but it will give you a TLE, so it's better we just make sure to have a 2D array. So in C++, this is how you basically declare a 2D. In Java, people just can carry what to say, just you can carry a 2D array that will work. Just carry a 2D array. In C++, we have to declare the sizes. That's why there's a problem in carrying 2D arrays. Otherwise, I would have done. So first step is this, right? Next step is initializing. How's the next step? Checking if that state has been previously computed. Done. So what I can say is let's quickly run this off. Should be fine. Okay, we get some problem. Oh, we're not passing a DP here. Let's quickly pass it. Okay, we get a wrong answer. Why is that? Okay, we have assigned mn. So yeah, sorry, that's my bad. Let's do it m and n. Yeah, working fine. If we submit this, so that's the first time I'm submitting. Cool, time limit exceeded. So it still says time limit exceeded, probably due to the stack space that we are using. So let's quickly optimize this portion and try to have it as 2D arrays int dp of mn. And I know one thing for sure, the number of states will be something like I equal to 0, I lesser than m. Again, Java people, please don't cry. It's the exact same code. So if you're Java, you can also follow this. J lesser than J plus plus. We know one thing, if I is equal to 0 and J is equal to 0, you can be like dp of I, J is equal to 1. Else you can be like, you can assign an up 0, you can assign a left as a 0. If I is greater than 0, then there will always be an up, which is dp of I minus 1. J, if the J is greater than 0, the left will always be dp of I of j minus 1. At the end of the day, instead of returning dp of ij equal to, you can say up plus left. So as simple as that. And what's the answer? Where's the answer stored at, guys? The answer is definitely stored at return dp of m minus 1 n minus 1. So let's quickly run this off. Should be fine. Runs. Let's submit this. Let's see if we are getting a TLE now. Okay, it's still giving time limit exceeded. Interesting. The time complexity is m cross n. Okay, fine. Let's optimize this. Let's further optimize this and let's see. So what did I say? How to space optimize this? The space optimization is quite simple. We can say temporary of the number of columns. The number of columns are n. You can definitely do 0. So instead of temp, just make sure it's a previous DP, right? And over here you can definitely have vector of int of temp, which is the current row that is being computed, because this is the current row which is going. So kindly have it as 0, right? Now can I say this is, if I is equal to 0, j is equal to 0, you're computing the current row. So the current row is now temporary. Understand, the current row is now temporary. So temporary of j will be 1, right? Instead of up left, let's try to write this. Instead of dp of I minus 1, what is I minus 1? The previous. What is dp of I? The current, which is temp. Correct? So if I name it better, you probably can name it current. So the current is this. And that's it, perfect. And once you've computed the temp, yes, once you've computed the temp, what you can do is, you can say, okay, fine, I've computed the temp. I can be like, now I can just swap it. I can now swap it, because the current guy, when I will increase, it will become the previous. So previous will be current. And can I say the answer will be stored at, what is this? M minus 1. This previous. So in previous is n minus 1, the answer will be stored. So if I run this, it should be fine. We are getting a dp was not assigned. Have I defined? Okay, sorry, that's my bad. So dp of I means temporary or current rather. So we just run this, you see this running fine. And if you submit this, it will again not be running all the cases. And the reason is quite simple. It gives me 91 score and everything is not running. The reason is, I'll tell you. So if you Google the same question, grade unique paths, take it forward channel itself, you'll find a solution which is of combinatorics, and the time complexity is big of a number of columns or number of rows, whatever you wish to. And it works in better than m into n. That's why we were getting the TLE. I'll not teach this. You can definitely watch this video again. Like this video I've already recorded, so you can watch the solution over there and you can try submitting it. So why did I teach this question in complete DP? Because I wanted to teach you DP, not how to solve this problem. The concept was to teach you recursion in 2D, then memoization in 2D, then tabulation in 2D, then space optimization in 2D. And I'm very much sure that you have understood each bit of this lecture. Just in case you have, please make sure you like this video, and if you're new to this channel, please do consider subscribing to us. It will be of immense help. And as our tradition goes, if you've understood this lecture, in the comment section, put up a understood comment. That will do me a world of good. And with this, let's wrap up this video. Let's meet in the next one. Bye bye, take care.